Hi guys, my name is Ashreen and I will be taking you for the N5 math course. If you are also doing the N5 physics course, I am also taking that course. So today we are just going to be doing the lecture for the 26th of September. I know quite a few people have issues with attending uh, face-to-face classes, so these online lectures will hopefully get you through the course well. And of course, if you guys need any help further than what we are providing you with these courses, you're more than welcome to message us on the group chats or even send us emails. We will be seeing you on the Saturday classes. It's more of a touch session really, so whatever questions you have during the week, you can either ask us during the week or when you see us on the weekend, you can ask us then. So yeah, once again, my name is Ashreen, and we're just going to do a brief overview of the course. So, like in all the engineering subjects, we have to get a 40% ICAS for you to be admitted into the final exam set by the department. So, from your ICAS, test 1 is about 30% and test 2 is the majority of it. Test 2 is more of an exam. So, the NATED manager Avinash, I'm sure you guys are all familiar with him. He is taking you guys for chemistry and I think chemical operations, if I'm not too sure. Yeah, so he told me that test 1 is going to be out of 50 and it can either be 1 hour or 1.5 hours depending on the level of the test. And then I'm assuming test 2 is going to be similar to an internal exam, which is about 3 hours. So that's the assessments out the way. And for your syllabus, we have 6 chapters here, so hopefully it isn't too hectic and hopefully we do have enough time. But I think with the online classes, it helps us manage our time better, not just me as a facilitator, but us as a class. I know some people learn differently at different types of day, and this enables you to learn best whenever it's suitable for you. That being said, chapter 1 is limits and continuity, which is what we're going to be doing today. And then we have differentiation, applications of it, integration techniques, applications of definite integrals, and differential equations. So first of all, we're just going to be doing a little bit of revision on limits from your N4. I know it's probably been a few months since you guys have been N4 and you would like a refresher. So the first law I would say is as x tends to a of the function fx, you simply need to substitute the x for the a since that is the limit and you'll end up with f of a. That one's pretty much self-explanatory. You just directly substitute a into x's place. For the second law, we have once again the limit as x approaches a. We have k fx. Now the k will act as a constant. Now because it is a constant, we are allowed to take it essentially out of the bracket, and all we have to find once again is the limit as x tends to a of f of x, which then just goes back into the first law, and then you multiply that by a constant, which is k. The third law states that if you have a sum or a difference of two functions, those two functions being fx and gx, and if you have to find the limit as x tends to a, all you have to do is find the limit as x tends to a of one function, then you can add and subtract the limit as x tends to a of the second function. Once again, everything here on this slide basically goes back to the first law. Having these on hand will really be on handy. So when I see you on Saturday, I'll make sure to print out a set of these and have it typed up nicely for you so you can refer back to it. I refer to these as cheat sheets, and in this chapter alone, there's going to be about 2 cheat sheets, if I'm not mistaken. So we have our laws continuing. The fourth law says if we have a product of fx and gx, and we have to find the limit as x tends to a, all you need to do once again is find the limit as x tends to a of fx, and the limit as x tends to a of gx, and you multiply the two. Similarly, for number 5, there's a fraction of fx over gx, and we have to find the limit as x tends to a once again. All you do here is once again find the limit as as x tends to a of fx, and then divide that by the limit of gx as x tends to a. The rest is also pretty self-explanatory. So for number 6, we have a third, and we have it to the nth root, and in the root we have fx. So what we can do is we can actually find the limit as x tends to a of fx, and then put that to the nth root. The seventh law states, as x tends to infinity, the function here being 1 over x, it is equals to 0. And if we have law 7 and 8 basically state the same thing. If we have x tending to the infinity of anything, regardless of the numerator, and x is in the denominator, it will be equal to 0. The last law states that if a constant, if x tends to a of a constant, if x tends to infinity of a constant, it is simply equal to the constant. So that concludes the revision N4 for the limits. Once again, this is the first cheat sheet. We're going to go right into the second. So on this slide, we have the cheat sheets. So on your left hand side, you have the function given here. And on the right hand side, you have the differentiated format. So instead of you, I wouldn't say manually, but individually differentiating each formula that you've been given, if you find the question on the left hand side over here, you can just refer to what it is on the right hand side, and you can just put that into your equation. So I think the first few here are self-explanatory, but over here, like once you start getting into your lins, your logs, and then your trig differentials, it just becomes handy to have these as a cheat sheet. Once again, this is N4 revision, and I'm not going to spend too much of time on it, but I will make sure to have this ready for you guys when you come in this weekend. So this goes on to the next slide as well, and it's just a continuation of the trig differentials, but there is also the product rule and the quotient rule. Number 13 is just the continuations. Number 14 and 15 is the product rule and the quotient rule. The product rule here is actually very interesting, as well as number 15. So for the product rule, I'm not too sure if I've done this in N4, but to find the differential of fx and gx, we take fx multiplied by the differential of gx plus gx multiplied by the differential of fx. And then for the quotient rule, it's similar, except this time we will have it swapped around. So it'll be gx multiplied by the differential of fx minus fx multiplied by the differential of gx all over gx squared. These two seem complicated now, but once we use it in practice and use it in examples, it'll be much easier. Right into some examples. So this is still a part of your revision form in full, but we're going to just refresh our minds a little bit. So for example 1, we're just going to do our direct substitution. So it says here to determine the limit as x tends to 3 of this function here, which I'll just refer to for now as fx. So since this is just a normal simple direct substitution, you just take or you just replace your x in the function with the limit given, which is 3 in this case. So here you just can put your x's here and here, so you replace that with 3's there and there. 3 squared is 9, so you have 9 minus 1 over 9 plus 1, and that ends up being 8 over 10. Simplified, you have it as 4 over 5. this example was just, just to remind you guys how we're going to do things, and we have harder things on the way, such as in example 2. So in example 2, we are asked to determine the limit of f of x as h tends to 0. And you can see in fx, we have, in the numerator of the given function, we have even more fractions. So we have 1 over x plus h minus x over h, all of that over h. Now, if you guys are, if we're going to just use direct substitution, and we say wherever we had h, we're going to substitute that with the 0, we're going to just end up getting 1 over x plus 0 minus 1 over x, all of that over 0. Now, if you simplify that, you have 1 over x minus 1 over x over 0, and that ends up being 0 over 0. Now, of course, this is impossible, so instead, when we get something like 0 over 0, what we need to do is manipulate the given equation so that when we substitute our x tends to whatever or h tends to whatever, we are not left with this. 0 over 0 is called an indeterminate form. So what we need to do is manipulate the equation. So what I did here is, when we're working with the numerator of the function as a whole, we found the lowest common denominator between this and this. And that ended up being x and then x plus h in brackets. So we do the straightforward multiplication here. And because we have x plus h in this, we just have to multiply it by x on this side. And because we had x on this side, all we have to do is multiply it by x plus h. And then that ends up just being, when we simplify, that will be x minus h over this, and all this over h. So as we said that here, we simplified it over here. Now that is negative h over x squared plus hx. The x squared plus hx, of course, comes from you multiplying this x into the bracket here. And when we do that, we are left with this. Now we know it'll just be much easier if we multiply by the inverse of h. In this case, it'll just h. So the inverse of that is 1 over h. And when we do that, the h here and here will cancel out one another, leaving 1 over x squared plus h. Now we know that h tends to 0, so we just substitute that in, and then we are left with negative 1 over x squared. So for example 2, we're doing rationalization. So here we are asked to determine the limit as x tends to 3, and our function is x minus 3 in the numerator, and in the denominator we have some surds. The first one being square root of x minus 2 subtracted by the square root of 4 minus x. So if we were to substitute the limit, which is 3 in this case, right in, we would once again get an indeterminate form. Now, of course, we can't do anything more with this because it's literally impossible. So we need to manipulate the given function so that we don't end up with 0 over 0. The way we do that is multiplying by the denominator, but the positive of it. And the way we keep that mathematically correct is we multiply the given function by the opposite of the denominator, but on the top and the bottom, so in the numerator and the denominator. We do this because if you put this in brackets here, and if you put this in brackets here, it's equal to 1 because it'll cancel each other out. And multiplying by 1 still just leaves the function by itself. So it's very easy to make a mistake here because in the given function we have a negative in between the two surds, but because we are rationalizing the denominator, we have to use the thirds over here as well. So if you're doing this in a rush, these signs might make you will not confuse you, but if you're rushing, you are bound to make small mistakes. So that's something to look out for. So after we rationalize using this, all we have to do is multiply out. And once we do that, the numerator is straightforward because you can't really simplify anything in the numerator. So it'll just be x minus 3 in brackets multiplied by these thirds over here, once again in brackets. And because we rationalized, the thirds in the denominator are now gone. So we have to multiply the square root of x minus 2 by itself in this part, in this term. And then we have 4 minus x here. It's a point to note that the multiplying out in the denominator is essentially using the FOIL method, but because it is square roots, you don't see any of the squares here. So if you do so in FOIL, if you have the outers minus the inners, it will cancel one another out because here's a negative and here is a positive. So once you multiply the denominator out here, you are left with it's going to be 4x multiplied by whatever, and once you simplify this, you end up with 2x minus 6. Now the first rule when you're going to factorize is you have to take out the highest common factor. In this case it was 2, and once we do that, we can see that you are left with x minus 3 in the denominator. You also have x minus 3 in the numerator, and those will cancel each other out, as we can see here. And now we are left with just thirds in the numerator of the function. And now when we substitute our limit, which is x tends to 3, we can see that this here will give us 3 minus 2, which equals to 1, and here it will say 4 minus 3, which is also equal to 1. So the square root of 1 plus the square root of 1 is simply 2. And once again, all this is over 2, and so your final answer is 1. So for our fourth example, we will be doing the division by the highest power. In this example, we are asked to calculate the limits as x tends to infinity, and our f of x has, it's a fraction once again, and this time it has x cubed in both the numerator and the denominator. I forgot to mention this earlier, but before I go through the example, I have it laid out on a slide by itself for you to attempt it. So if you guys want to do that, you can obviously pause the video and do that. So I'm just going to carry on over to the next slide. So in this example, all we have to do is divide each term in the numerator and the denominator by the highest power. In this case, in both the numerator and denominator, the highest power is x cubed. So all we will do is divide each and every single term by x cubed, and that ends up leaving a lot more fractions than what you started off with. But it also simplifies the highest powers. So in this case, it was x cubed and 5x cubed. And once you do that, you are left with a whole bunch of fractions here as well as here, but these are just left as the coefficients of the x cubed. Now, if you can remember from our first cheat sheet where we saw that anything over x is equals to 0, where if x tends to 0, that is the law that we will use here. So because we use that law, this ends up being 0, this ends up being 0, this is also 0, as well as this. So if all of these things are 0, you are left with 1 over 5, and that is our final answer. Now we'll be moving into L'Hopital's rule. This is essentially the foundation for the rest of the module. It's going to be used a lot in at least half the chapters and up until we get to integration. So if you don't understand this now, please let me know. You can send me a message on the group chat, or you can just tell me when you see each other this weekend for me to go over this in like detail. So this is L'Hopital's rule, and it states that if you calculate the limit as x tends to a of fx over gx, it will equal the limit as x tends to a of the differential of x over the differential of gx. And this goes on right up until, you know, however many differentials you want to have of that function. So it works with the first differential, the second differential, right up until whatever. So in this example, we have to determine the following limits. So we have to determine the limit as x tends to -3 of fx, and in this case, fx is x cubed plus 27 over x squared minus 9. Once again, pause the video, try doing it by yourself. So if we directly substitute our limit, which is x tends to -3, if we input that, we once again get an indeterminate form of 0 over 0, and you know we can't have that. So if you ever substitute and you get 0 over 0, you know that you have to manipulate the equation further. So what we will do here is use L'Hopital's rule. If you want to use L'Hopital's rule, you will need to explicitly state that, like the way I said here, use the rule. So what we'll do is we will differentiate the first function, which was x cubed. Let me just get my pen out here. So if we have a function, please excuse my handwriting. So if that was our function, in the numerator it was plus 27. When we differentiate using the shortcut method, because once again using first principles here will you'll never finish a paper if you use first principles. So we know to do the shortcut, we take the power, which in this case is 3, and multiply it by the coefficient of x. In this case, there is a coefficient of 1, so we say 3 times 1, which is 3. Then we have x. Then we have the power, so we have to subtract 1 from it. So 3 minus 1 is 2. And then because this is a constant, we don't add anything. So that's how I got this. Similarly, that's how we ended up getting 2x out of the original denominator, which was x squared minus 9. So once we do that, we can substitute our limit in, which is x tends to -3. And once we do that, we get 27 over 6. So this is the last example we will be doing today. We will be doing more on Saturday, so if you guys are unable to attend, please let me know so that I can personally send you all the notes that we're going to be doing then. Because we haven't done too much, I will not be doing a tutorial session per se. We will just be continuing everything that we have done. So in the final example, we have the limit as x tends to infinity of our function, which is 3x cubed over e to the power 3x. This example, if we substitute our limit, which is infinity, directly, we end up getting infinity over infinity. Of course, this is an indeterminate form and we need to manipulate the equation further. So we can do that by differentiating the numerator as well as the denominator. And in this case, we are treating the numerator and denominator as separate functions, as seen by L'Hopital's rule. So what we're going to do here is multiply. Let me get my laser pointer out quickly. So we're going to multiply the numerator, which is 3x cubed. When we multiply that, we end up getting 9x squared by using the shortcut form of differentiating, where we take the power multiplied by the coefficient. That's how we get 9, because it's 3 times 3. and then we get the 2 by subtracting 1 from the power here. Then in the denominator, we differentiate that as well. And if you use your cheat sheet from earlier slides, it was the second cheat sheet, number 3 on the list. We can see that to differentiate a function containing e, all we need to do is bring the constant in the power as a constant overall. And that's how we ended up getting 3 over here. Right. Now we can simplify because 3 goes into itself once here and it goes into 9 3 times, and that's how you end up with this function. But now if you substitute x here, we will once again still get infinity over infinity. So if that ever happens, you need to carry on differentiating, because remember L'Hopital's rule says any amount of differentials will still equal to the same limit. So that's where we were. So we're going to carry on differentiating the numerator. So we take 2 multiplied by 3, which ends up being 6, and when we subtract 1 from the square here, it ends up just being 1. Doing that in the denominator as well, we basically end up with the same thing as previously, because the denominator didn't change much. That's one of the things to note about differentiating a function that has e in it. So once again, we can simplify because 3 goes into itself once, it goes into 6 twice, and that's how we end up here. Now if we have to substitute our x equals to infinity here, we will once again get an indeterminate form of infinity over infinity, which means we need to differentiate one more time. And if we do that, we can see that 2x differentiated is simply equals to x. And then in the denominator, the e to the power 3x is still just equals to 3e to the power 3x. And once we substitute our x tending to infinity, we are left with 0. And that is all for today's class. We will continue doing some examples in Saturday's class because there are a lot of examples involving trig, and for that I would rather see you face to face so that we can discuss it. Also, we will be doing continuity as well. It's a very short and easy part of the chapter. You guys will get it very quickly. So yeah, I hope to see you all day on Saturday, and I look forward to meeting you. Thank you for watching today's lecture.